In this tutorial, I will be demonstrating the steps of constructing a DC motor and will also explain all the relevant principles which allow the motor to spin. DC motors are found in many toys and appliances which have moving components. The main components of a DC motor are a rotor or armature, a stator, commutators, brushes, an axle, and a DC power supply. Each component plays an important part in allowing the motor to spin. The following materials were used during the construction of this motor. The following table shows the risks that were present during the construction, as well as strategies taken in order to minimize them. Each component has a special function which allows the motor to spin. The commutator is a split ring which assists in reversing the direction of the current through the motor after every 180-degree turn, which allows for a better flow when turning and ensures that the torque is in the same direction. The axle is attached to the armature and is the pivot point used to transfer the mechanical energy onto the object connected, for example, a fan. The coil is a shiny copper wire which you wind a number of times around the armature. When current is passed through the wire, the coils will act as an electromagnet and will have two poles which will attract and repel from the permanent magnets that will be placed on both sides of the motor, thus providing torque to the axle. The brushes are the means of passing current from the power supply to the coils via the commutator. The external magnetic field consists of two neodymium magnets and is used to apply attractive and repulsive forces towards the electromagnet, allowing a spinning motion and generating torque. The armature is the frame on which the coils are winded, and together the armature extends and connects to the commutator. And finally, the power source is used to allow a current to pass through the wire and make the coils an electromagnet, allowing the torque to be generated through the motion of the rotor. Next, I will demonstrate my method of creating my motor. After gathering all the materials, the first thing I did was cut the commutators. When cutting the commutators, I ensured to take care as the pliers are sharp. I cut two identical pieces which I measured by placing the copper bracket around the plastic dowel. I ensured that I cut them a bit short so that there is also a gap on each side of the commutator so that there is a split when the current is passing. Next, I drilled a hole for where my armature would be placed on the plastic dowel. I held the plastic dowel down and took care while drilling, also ensuring the hole is straight and in the center of the dowel. Then I started to wind the coils. I stretched the coil and found the center. After putting the center in the middle of the bolt going across the shaft, I began to coil on each side, ensuring that the windings were going clockwise on one side and anti-clockwise on the other side, and ensuring that there was the same amount of turns, totaling to around 350 turns on each side. The final coil should look something like this. I then sanded the coil and the commutator area where I would join them. This ensures that the conductivity between the two will be good, as the enamel covering may affect the conductivity. After sanding, I wrapped the coil around the commutators a few times before using a hot glue gun to glue the commutator to the shaft, ensuring that the split between the two commutators are in line with the bolt. Next, I put the shaft and the base together and held the bearings in place. First, a larger shaft was put through the hole in the base. Then I inserted the smaller shaft with a bolt and coil through the larger shaft. I then screwed in two bolts on the edge of the base on the outside and inside, so that the shaft doesn't move around while the axle is spinning. This also reduces the friction between the shaft and the base, thus allowing a smoother turn. The next step was to install the stator or the external magnetic field. This was done by screwing 2 steel brackets into the base in line with the armature. The last step was to connect the brushes. I sanded both ends of the metal wire to ensure electricity is conducted properly, and then held them in place by screwing them into the top of the timber. Now for a first test. While the first test was successful, I noticed that the speed of the motor was very inconsistent. I discovered that the brushes were not consistently brushing against the commutators, so I decided to bend the end of the brush which goes against the commutator. This will allow for a larger area, meaning that the brush would more consistently go up against the commutators, allowing for a more consistent speed. My final product looked like this. Next, I will explain the physics principles which allow the motor to spin. Magnetic flux is the amount of magnetic field that is passing through an area. It is shown by magnetic field lines between the north and south poles of the external magnetic field. The formula for magnetic flux is magnetic flux equals BA cos theta, where B is the strength of the magnetic field and A is the area affected by the field. Maximum magnetic flux is achieved when the magnetic field B and the area that is affected A are parallel as shown in the formula. This is shown in the photo below as the coils turned magnetic flux will decrease as the angle increases right before the current alternates when the brushes switch commutators or when the magnetic flux is at a minimum. This is shown in the photo below. Zero magnetic flux is achieved when the area and the magnetic field are perpendicular to each other. The DC motor turns due to the production of torque. Torque is the turning force on the motor and is produced when current passes through the coil, which is affected by a magnetic field. The formula for torque is torque equals NIAB sine theta, where N is the number of turns, I is the current, A is the area affected, and B is the strength of the magnetic field. These variables are the factors that affect torque. By increasing the number of turns, the current, the area that is affected, or the magnetic field, torque will always be increased. The following image shows max torque as the area when it is perpendicular to the field. Torque is minimum right before the current alternates as shown in this image. The magnetic field strength has a large effect on the torque as it is a variable in the formula. The magnetic field is a variable which induces a magnetic force on the armature once it becomes an electromagnet. Back EMF is the electromotive force which opposes the changing current which induced it. This means that it limits the current flow, which limits the speed of the motor. When the motor starts, the back EMF is small and the current flow is large. Back EMF gradually increases as the motor runs, decreasing the current flow and stopping the coils from burning out. As the motor speed increases, the back EMF will increase to keep the current flow low. Faraday's law states that the EMF in a current is directly proportional to the rate of change over time of the magnetic flux in the circuit. This tells us that by increasing the magnetic flux or by increasing the number of turns of coil, we are increasing the induced EMF. The formula for Faraday's law is the negative number of turns multiplied by the change in flux over the change in time, which equals to the induced EMF. Lenz's law states that any induced EMF will give rise to a current and create a magnetic field that opposes the change in flux. This demonstrates the principle of conservation of energy. The law also explains the direction of the voltage within the motor as the current changes. As the coils spin, some of the mechanical energy from the field will become electrical energy, which will oppose the current and therefore make the current flowing smaller. This ends my tutorial. I hope you learned something and thank you for listening.